All right, let's talk about resistance and let's get practical really quickly. Let's say we want to make a circuit with this LED. This LED came with a paper that says that it doesn't want more than 20 milliamps. So we need to figure out how to make sure that it only pulls 20 milliamps. So first of all, we should talk about what a milliamp actually is. An amp is a unit of current. So I'm going to put current here. And the unit of measurement is an amp. It's really an ampere, I think. So this becomes an amp, and it's abbreviated as A. Now, this LED only wants 20 milliamps. An amp, we could say, is equal to 1,000 milliamps. And our LED only wants 20. So what that means is we need to pretty much figure out if our power source by default is going to give more than 20 milliamps. Because if it's going to give around 20 or less, then I guess we don't need to resist it. So my power source is this little plug. And if we zoom in, it's kind of like a multi-power. It's pretty cheap. And I have it set to 3 volts. And we can see the output here has 3 volts. Well, it has all these different settings depending on what we set it to. I set it to 3 volts. And then it has 2,000 milliamps max. Or we could say it's 2 amps maximum. So this output is going to put out 2 amps or 2,000 milliamps, which is 100 times more than this value. So that's a problem. So we definitely need to reduce the current. So with that said, we know that if we plug this into our power source, we have 3 volts coming through here, as well as 2,000 maximum milliamps. So if we were to plug in our LED, then the LED would probably explode because it's 100 times more current than what it wants. So what we need to do is figure out how can we reduce the current here from 2,000 milliamps down to 20 or less than 20. And the way that we do that is through resistors. This is a resistor. I don't really know what kind of resistor it is. I'm still a beginner at this stuff, but I know it's kind of a conventional and a basic resistor. So resistors have values, and those values are measured in ohms. So let's get back over here. So we have our current, and then the next unit we're going to say is resistance. And this is measured in ohms. The abbreviation is, I think it's just R for resistance. So it's R. And the symbol for an ohm is the omega Greek alphabet letter. So this resistor that I just had, this is a 1,000, and then I'll put the ohm symbol, ohm resistor. Or we can call it a 1K. 1K, either ohm or the symbol. You can do either one. So this is a 1,000 ohm resistor. So what we need to do, just as a starting point, is figure out, well, if we connect this resistor, right, our 1,000 ohm resistor to, and then let me write down here, we have our voltage, of course, which is measured in V, and we have 3 volts. Okay? So we need to see what happens when we connect our 1,000 ohm resistor to 3 volts. Then it's going to give us our current. So we can think of it as the current, right? By the way, the current, for some reason, the abbreviation when we're dealing with it in formulas is I. I don't really know why. But anyway, so what we need to do is figure out if we have our 3 volts here and we have our 1,000 ohm resistor, how much current is going to flow. So the way that we do this is we'll put current is equal to the voltage divided by our resistance. Okay? So in this case, it's pretty simple because we know it's 3 volts and we just divide it by 1,000 because that's our ohms. And this is going to give us an amps result, a current result. So volts divided by resistance equals current. And in this case, it's 0 point, and then how many decimal places do we move this? 1, 2, 3. So we get 0.003 amps. Now, if we multiply this by 1,000 to get milliamps, because 1 amp is equal to 1,000 milliamps, then this just becomes 3 milliamps. Is that on the screen? It is, right? Yeah. So 3 milliamps is much less than 20. So we should try that. So let's see if this works out. Let's always like to get practical as quickly as possible, although it's already been a couple minutes. And let's see, you could just plug it in anywhere here. All right. So our resistor is in. So we're pulling power, right, from the 3 volts source into row 15 here. And now we just need to put this to ground to make a circuit so that we can actually have current flowing. So let's ground it with this blue wire. So we can plug this in and let's put it to ground. So this is a complete circuit, right? We have power through the resistor, and then it's going to go back to the negative to ground. So what we want to see here is make sure that this guy is only pulling 3 milliamps. So I'm going to plug in my actual power over here, a 1 and a 2. And we can't really tell that anything's happening. So what we have to do is use our meter. Get this little guy, make sure he fits on the screen. And if we measure the voltage, let's put our positive probe to the side. That's positive. Can you see that there? I know the wire's in the way. So it says 3.3 volts. So right now we're reading voltage and not current, because voltage is easier to read than current. But what we'll do is we'll break this open and see the current flowing. So we know, let's just write down what we know. So we have, in this circuit, our voltage running through the resistor is 3.3 volts. And the way to calculate, this is where it gets confusing for me, but we'll just work through it together. We can basically calculate the current because we know 2 things. We know the voltage is 3.3 volts running through it, and we know the resistance value because it's written on the packaging. It's 1,000 ohms, and we can also measure it. So if we have the voltage and the resistance, then we can do a division. So if we divide this, right, by the 1,000 that we know that the resistance is, then we get 3.3 milliamps, right? Because we get 0.0033 amps, which is 3.3 milliamps. But rather than trusting the mathematics, let's actually try and measure it. So what I'm going to do is move this just off to the side so that it's kind of floating. So this guy is sticking up. And then what we can do is we can change our meter to read current, which is over here. So I'm going to just put it on one of the lower settings, like 20 milliamps, I guess, which is just the range, I guess, that it'll pick up. And if we put our positive on the resistor and our negative on the wire that's exposed that goes to ground, so basically what we're doing to read the current is we need to make sure that all the current has to flow through our meter. That's why we had to break these apart and go in between them. To read voltage, we could just do it without affecting the circuit. But to read current, we have to make sure all the current's flowing through our meter. And we can see right now that it's 3.32 milliamps because we have it set to the small little m, right? So this is taking it in the units of milliamps. So we have 3.3, which lines up I mean, almost exactly with the math. So that works. And the cool part about this is we can kind of see a pattern here. We have current, voltage, and resistance. Once we know two of these, we can figure out the rest. But before I continue here, actually, what we should do is get our LED working, right? Because I think that's what I would want to see. So we know that with this resistor going to ground, it's a safe level for our LED. Because remember, he wanted 20 milliamps, and we're down to 3.3. So we're all good there. So let's plug in the LED, which I don't know where I put him. I think he's over here. All right, so let's plug in his long lead, right, the positive, to where the resistor is bringing in that power. And then we can also kick up this guy so that we can connect it manually and take another reading to make sure that our milliamps are still at a level that we want. So I'm going to get my meter again, put it back. Let me zoom out. And let's get our positive on the LED. Let me put it back to the milliamp setting. Right now it's on micro, which is even smaller. So I'll just put it back to milli. So if we attach this, then we'll see the LED illuminates. But you can see that the milliamps have dropped significantly. It's now down to 1.5, it seems, right? And the reason why that happened is we know that resistance lowers the current, right? So we have our 3 volts here. We divide it by 1,000, which is our resistor value, and we get 3 milliamps, which should be running through here. That's how much current is flowing. But what I didn't say or remember is that the LED itself has its own resistance. So that's why we went from 3 milliamps down to 1.5, because he has is own resistance that we would basically add to this value to drop it down to 1.5. And we can use algebra to figure that out. It seems to me that this has about 1,500, or is it just 1,000? I don't know what it is, but we could figure it out. But I'm going to move on to kind of expanding on this. So we see that when we know 2 of these, we can figure out the third one. So it makes sort of a triangle. The V goes at the top, and I'm going to say I because that's the abbreviation for current. I don't know why. I don't know why it's not C, but whatever. And then we have resistance. And this makes kind of an Ohms triangle. And it makes it really, really convenient for us to figure stuff out. So let's say that we want to know the voltage, okay? So right now, we know that we have 1,000 ohms in resistance, right? At least on the basic circuit. So let's take out the LED. So we have 1,000 ohms here. We have 3 volt source. That's all we need to know. So we have, what are we trying to figure out? If we want to figure out the voltage, sorry. So we don't know this is 3 volts, right? Let's pretend that we don't know that. So we know that we have 3 milliamps. And we know that we have 1,000 ohm resistance. So if we want to figure out V, we just multiply these two together. And we multiply them because they're next to each other. So we can say V equals IR because these guys are next to each other. And when they're next to each other, we can pretend this is a multiplication, right? That there's an invisible sign there. So voltage is equal to I times R. We know that our I is 3.3 milliamps, but we should probably convert it to amps. So let me get my calculator on my computer here. So 3.3 milliamps divided by 1,000 is 0.0033. So we have equals 0.0033. And then we're going to multiply by our resistance, which we know is 1,000. And we can measure it with a multimeter if you want, or, normally the packaging is accurate. So we're going to multiply this by 1,000. So 0.0033 times 1,000, I mean, it's pretty easy because we just divided it by 1,000. So 0.033 times 1,000 is equals to 3.3 volts, which is exactly what we measured. So let's say we want to figure out current, right? Let's say we didn't know what the current is. So I think we did that before here, right? And we could see current is equals to V over R. And this makes it easy. Current, and we look at the other two, well, V is on top of R, so that's all we do, equals to V over R. And in this case, we know it's 3.3 volts, because we measured it, and we know that there's a 1,000 ohm resistor. So again, we get 3.3 milliamps, right? Really, we get 0.0033, but we multiply it by 1,000. And then let's say we wanted to figure out our resistance, and this is what we can do for the LED itself. So R is equals to V over I, right? Because R, and then we look at the other two, well, V is over I, and I is current. So if we do 3.3 volts over 3.3 milliamps, or really it's 0.0033, then we do 3.3 divided by 0.0033, and we get 1,000. So this is really 0.0033 amps, and we need to work in amps, not milliamps. So we divide 3.3 divided by 0.0033, and we get 1,000 ohms. So it's a bit boring, but it just shows that you can figure out any one of these by the other two. So that's how we limit resistance to protect components. So let me write that down actually. So there's two main uses for resistance, right? One of them is to protect components, just like what we did. The LED only wants 20 milliamps. We need to figure out how to limit the current to 20 milliamps. The other method, now let me connect this back into a complete circuit so we can do some testing. So let's plug in our ground. Okay, so the other thing that resistance does, and this is, and this is the most widely used approach, is it directs a flow of current. So right now, I actually don't have. Okay, sorry, this wasn't plugged in properly. All right, so this is working now. The other main use of resistance is to control the flow of current. And the way that we can demonstrate that is, let's say we had this circuit right here, right? We have, let me zoom in again, sorry. All the zooming in and out. So we have power, again, coming from the resistor, limiting the current to 3.3 milliamps. And the LED is on because it's connected to ground. So we have a full circuit here. Now, what would happen if we connected another wire to where the LED is getting power from the resistor? So let's plug this in. And then I'm gonna ground this. So we can see that the LED turned off. And why is that? The LED is connected first, right, to the resistor. So we have power coming from the resistor. It should be going through the LED and then out to ground. So what's happening here? We can see that when we disconnect this second circuit, it turns back on. And this is a real foundation of electronics, where the electricity is going to take the lowest resistance path to ground, or we could say the cheapest path to ground is what I tend to say. I don't know how accurate that is, but in other words, electricity is coming through here, and on this line, he has two paths to take. So this is a parallel connection because he has two different paths to take. One of them is pretty high in resistance. As we saw earlier, it dropped our current from 3.3 volt milliamps down to like 1.5 milliamps. So this guy has a lot of resistance. And this wire itself has nearly no resistance. So we can take some readings and kind of figure out what's happening. But basically, since there's resistance this way, as soon as we connect this other path, all the current drops out of the LED and takes its way home. So by using resistance, we can choose which way the electricity goes. We can try and turn back on this LED even with this parallel connection by adding more resistance on the path. So why don't we, how can we do this? Let's connect this guy back in. And then what I'm going to do is add another resistor right here. So let's connect this 10,000 ohm resistor, which is a lot, and see if it turns back on our LED. So right now we have power coming through our main input, you could say, our pull-up resistor, I think it's called. And then it has a path to go through, either through the LED or through this other resistor. And so we can see right now that we don't really have a path yet because this resistor is not plugged into our wire. So let me move this over and see what happens. So we can see that right now, I have to change out this wire because the other one was kind of messed up. But we can see that right now, even though we have this path to ground, this secondary path, the LED is still on because this resistor is basically blocking enough current that it's still going to flow through the LED. Why don't we swap out this 10,000 ohm resistor for a 1,000 ohm resistor and see what happens. So plugging this in with a 1,000 ohm resistor again turns off our LED because it's allowing enough current to come this way that no current really wants to go that way. And it's not exactly accurate for me to say that. There is current going through here, but not enough to turn on the LED to create the voltage required. So what we're kind of doing here is the essence of an inverter. By allowing another path to ground, we're turning off, we could say, our output. Let's say this is our output, because there's another path that's cheaper for the current to flow through. But by removing that path, the electricity is forced to go through the LED to go home. So by manipulating the resistance, we're really directing the flow of electricity, which is a super fundamental building block of logic gates and computing and basically everything. There was something else that I wanted to do here. Let's start taking some voltage readings. And, you know, we could break it open again and keep taking current readings, but we already know that we can figure out our current by just dividing the voltage over the resistance. So let's do another test. I'm going to plug out our alternate path to ground, which turns on our LED. And what I want to do is also show that our resistors will visually reduce the current flowing through our LED. So right now we know that we have 1,000 ohm resistor here. I'm going to take out the 1,000 ohm resistor, and I'm going to plug in this 10,000 ohm resistor, so it's 10 times more resistance. Wait, sorry, this is another 1K. I messed up. We could see by the brightness. So let's plug in this 10K and see what happens. And we can see it's much dimmer, right? And that's because we're reducing the current that much more. We can visually see that the LED is much dimmer because of the reduced current. And we can measure this, right? So let's take our let's take our meter and measure the voltage, what we'll call across this resistor. So right now we have 1.69 volts, which equates to, if we divide it, right, 1.69 divided by 1,000, or 10,000, I'm sorry, is very, very little. So we have 1.69 volts divided by 10,000. That's really tiny. So I forgot what it was. 1.6 what? Was it 69? Divided by 10,000. And again, we're doing this because we're trying to figure out the current, right? So we have I is V over R. So V, right? And then this is our resistance value, 10,000. So let me calculate that. 1.69 divided by 10,000 is 0.000169. If we multiply by 1,000, this is amps, right? Then we get 1, 2, 3. So we get 0.169 milliamps. And if we multiply by 1,000 one more time, we get 169 what we'll call microamps, which is just a smaller value. So our 10K is running 169 microamps, which is almost nothing. And that's why the LED is super dim. And a couple things to note, when we have what we call a series connection, which is one path to ground. So in this case, we have power coming through the resistor, going through the LED, and then going to ground. The current in a series connection is constant everywhere. So if we use our formula to calculate the current based on the resistance and the voltage, similar to what we did before, then we can get the current running through the resistor. And with that, we know the current running through the entire circuit. Another thing to know is if we add more resistors, you just keep on adding the resistance values, and that's what the resistance is. So for example, let's say that we're just going to use resistors in this circuit again. If we ground this circuit, then we can see that our voltage is roughly 3.3 again. And that makes sense. We have 3.3 volts, we have a 1,000 ohm resistor, so we get 3.3 milliamps, right? Or 0.0033 amps, but we just convert it to milliamps to make it easier to work with. So let's say we want to add another 1,000 ohm resistor to this. So let's move our connection to the side, our ground, and let's add this in right here. So what we have here is 1,000 plus 1,000. So we have power coming in through resistor 1, goes to resistor 2, which then goes to our wire that's grounded. So if we take this measurement on the same resistor that we had before, then we can see, oh wait, I don't think it's plugged in properly. All right, so now we can see that the voltage is actually 1.64 now. And this makes sense because our current was 3.3, but now we're dividing it by 2,000 ohms, right? Because we have 1,000 and 1,000. And 3.3 divided by 2,000 is roughly 1.65. And that's exactly what we're seeing here. So by adding another resistor in series, right? There's only one path to ground. You just add these up, and that's a total resistance for the series. And we could just divide our source voltage by that resistance, and we get our current, which in this case, we have 3.3 volts divided by, we could say 1,000 plus 1,000, right, equals 2K. And this is equal to 1.65 milliamps, or 0.00, I guess 165 amps. But I'm just simplifying it to 1.65. So we can keep adding resistors if we want to get to a certain value. But it's just important to know that, number one, sorry, I just shook everything. It's important to know that in a series, the current is constant everywhere. So in this resistor, it's whatever that is, 1.65 milliamps. Over here, it's 1.65 milliamps. And this wire even is 1.65 milliamps. And we can keep adding resistors in series, and the calculation remains just as simple to figure out the current. And again, we're taking the voltage reading across any resistor that we know its value. So what we could do, just to illustrate this some more, oh, my light is moved. Let me adjust it. So what we can do is we can continue to take voltage readings, but we can choose where we start and stop. So let's go from the start of the resistor to the end of the second resistor. And we'll see that we have our full 3.3 volts here. And that makes perfect sense. Because if we divide our 3.3 by 2000, we get the 1.65. Or we could take this resistor by itself, which is, we know it's a 1000 ohm resistor, and divide our 1.65, and we get the same result, right? 1.65 divided by 1000 is 0.00165 amps, which becomes 1.65 milliamps. So we can kind of see the math in live action here, basically, working the way that it should. So by taking the voltage across two of these resistors, it's basically getting the voltage difference. And we can see that both of them are consuming the same amount, which makes sense because they're both the same resistance values. Now, I'm not taking the values and stuff from the LED because from what I've been told, LEDs are very tricky and they actually have a variable resistance where it will change depending on the voltage going through it because it always tries to maintain 1.8 volts. So I'm not going to try and calculate the things for the LED because I think it's always changing, but maybe somebody in the comments can tell us more about that. When it comes to parallel connections for resistance, that's where it gets really confusing for me. But let's work through it together. So I apologize in advance as I stumble. Let's say that we're going to, instead of taking one power input from our 3.3 volts, let's say we take two. So we do it in parallel. So in other words, we have our, let's say 1000 ohm resistor. So we could put this guy in. And then let's say we have another one who's right next door. Okay. So we have, let me zoom in. So we have 1000 ohms or 3.3 milliamps coming across. And I guess we have another 3.3 milliamps coming across. And let's connect these together onto a line where it will be grounded. So we basically have a parallel resistance. So let's use this red wire to send this down. So we're taking the power or the current through this resistor and taking it to row 18. And then let's take the other one to row 18 as well, which hopefully maybe this cable is the right length. Yeah, it is. Okay. And then let's ground this and hopefully nothing explodes. Now in series, we know that we add up 1000 plus 1000 is 2000, but that's not the way it works with parallel. And don't let these wires confuse us. We're just basically making sure that both of these resistors end up connecting together to be grounded here, right? They both just connect to this brown cable. So we have power coming across, and both are leaving on the brown cable. So the question here is, how do we calculate the current flowing through this brown cable? Or this could be like an LED or a load or anything, right? But so we're trying to figure out, instead of having one resistor, if we have two of them of whatever value, in this case we have 1000 and 1000, how much current is flowing into our parallel circuit? And the way this is done is very odd looking. We basically use the reciprocal, and we don't need to know, I guess, all the words, although I guess it's useful. So for parallel, we take the reciprocal. So we take our resistor and we put it on the bottom underneath 1. So in this case, we have 1000 ohm resistor and we have another 1000 ohm resistor in parallel, meaning they both end up connecting at some point, right? So these guys are here and they both end up connecting essentially into this brown wire, and then they go to ground. So if we add this up, we get 2 over 1000. And then what we do is we get, I guess, the reciprocal of this, or we flip it back. So by reciprocating the values, we get not the resistance, but the conductance. Conductance. And this is my understanding of it. And this is just the way it has to be worked out. So when we have in parallel, you basically just add up your resistors, but you flip it and you put 1 on top. So we get 2 over 1000. And then what we do now is we flip it back to get our resistance. So in this case, 1000 divided by 2 is 500. So what we should be seeing here is 500 ohms coming through this point. And what we can do is we could break it open and test that. So let me take out this wire, if he wants to get out. And I'm gonna just stick him upwards like what we did before. So you can see he's up. And then I'm gonna put another wire in to the ground, which I think I have some, like a lot of wires from when I've cut resistors off. So let's just plug one of these in. Let me put that guy in so you can see him kind of sticking up there. And let's get our little dude and let's turn him back to measuring current. So we have our milliamps here. And let's just make this connection with our little dudes. And we can see that we have 3.3 volts. I think I'm wrong. Sorry, 3.3 milliamps. So I'm definitely wrong about this. I don't know where I went wrong. Maybe my resistor is not in properly. So let's take this again and see. So we have 6.5 milliamps, which is much, much higher than the 3.3. And remember, in series, when we have 2000 ohms, we'd be at 1.5 milliamps or 1.65 milliamps. In this case, we have 6.5 milliamps. So let's complete our math and see if that adds up. So in this case, where's my pen? In this case, we calculated our parallel resistance to be 500 ohms. So we know that if we have 3.3 volts over 500 ohms, right, will give us our current. So let me get my calculator. So 3.3 divided by 500 is 0.0066 amps, which is 6.6 milliamps. I'm kind of surprised that I calculated this correctly because it is very confusing to me. So let's measure it again, and just to double check, and then I'll go over what we did to make sure. So if we connect these again, we see it's 6.5. So we're off by a touch, but I think the point stands. Now, these cables do have slight resistance. So the more cables that we're using, I guess, is the more resistance that we're adding to the circuit. But we can see that in series, right? If we had 1000 ohm resistor and another one, then we would be at 2000 ohms, which would be 3.3 volts divided by 2000 would give us sorry, I'm not writing on the camera, would give us 1.65 milliamps, right? But we see that in series, it's totally different. We don't add it up like this. Instead, we draw a line, excuse me, and put a 1 on top of both of them. So in this case, 1 over 1000 plus 1 over 1000 is 2 over 1000, and then we flip it back. So we put the 1 on top of as many. So we might have 7 of these, right? We'd have 1 over 1000 and 1 over 500. Let's say we had a 500 ohm resistor. Let's say we had a 47 ohm resistor. It'd be 1 over 47. So we'd find the whole common denominator. We add them all up. We get our value, which is this. And then you just flip it, and then you solve. And that's the way it works for parallel. And if I'm missing something, somebody please comment. But this seemed to get us the correct answer. So that's the only complicated part, for me anyway, when it comes to resistance, is that parallel connection, because you have to do this weird sort of math to figure out how much is going through this point. So what this allows us now, one thing to my light's messed up. Sorry. One thing to note here is we can see that by series they add up and they get very high. So 1,000 plus 1,000 is 2,000. But if we put them in parallel, the number is actually lower than any of the individual resistors. And I assume it's because the current just has so many paths to go through. So if you need to sort of get to a number that is smaller than the resistors that you have, you can use parallel connections combined with series. Like you could do parallel and then series, and you can do all sorts of crazy mad scientist resistance, I guess, balancing and configuration. But right now I'm just trying to show that by connecting in parallel, you get a very, very different result. So I think that's the basics of resistance, right? We can reduce our voltage. Sorry, we can reduce our current based on how much voltage we have by controlling the resistance. So if we want to get to a certain current, then we can just solve and figure out the resistance that we need. Maybe we should do that right now. So let's say, because I think that's pretty useful. So let's say that let's say we want to do 20 milliamps, which is what the LED wanted. And we know that we have 3.3 volts. So let's see what it would be to get to exactly 20 milliamps. So let's redraw our triangle here. And we know that V is equal to I times R. So that makes it easy for us to remember. We know that we want to figure out how much resistance we need, right, to get to 20 milliamps. So R, and we look at the other two, well, V is over I, so it's V over I. So if we divide 3.3 divided by, and in this case, it's tempting to do 20, but really we need to do it in actual amps. So let's convert this to amps by divided by 1,000. So 1, 2, 3. Wait, is that right? No. See, I'm doing bad things again. Let's see. 1, 2, 3. Is it really that? Is there only 1 0? I thought there'd be 2 zeros there. I guess, no, I guess that's it. So 1, 2, 3. So it becomes 0.02 amps. So we're going to divide 3.3 volts by 0.02 amps. And the result that we get is 165 ohms. So the way this works is if we want to get 20 milliamps, we need to have 165 ohms of resistance. So I have a bunch of resistors, and let's see if we can add up to 165. So we have I have 47 ohm here, and then we have 100 ohm, and then we have 680. No, I need something smaller. So these 47 ohm resistors can get us kind of close. Let's see, what's 165 divided by 47? We need 3.5. So let's do 4 and see what we get. So we have 4 of these, and let's just put them in series, and we can add them all up, right? Somebody much more talented than me could very easily figure out in parallel a combination of parallel and series. So 1, 2, and I'm not cutting these just to make it easy, but I'll show it on camera a bit better. 3, and the last one I'll put to go home. So we have, I'm sorry, it looks so messy. Power coming out, then going into the second resistor, going into the third resistor, going into the fourth resistor, going home. So this is should be a working circuit. It's a series circuit. There's only one path to ground. And let's take our voltage reading and see what we get. So we get 0.8 volts. Seems very low to me. Let me connect it for the whole circuit and see what we have. So we do have 3.3. Oh, you know what? I'm forgetting. You see how easy it is to forget. It's 0.8, but not divided by 1,000. In my mind, I'm thinking divided by 1,000. But it's 0.8 volts divided by 47 ohms. So let's write that down. 0.8 volts over 47. And we're trying to get the current, right? So our current is equal to that. So we have 0.8 divided by 47. And we get 0.0017. So if we multiply this by 1,000, because this is amps, so we multiply 1, 2, 3, we get 7 milliamps. I thought we were trying to get to 20 milliamps. I feel like I failed somehow. It is. It's VIR. So we want to get current, V over R. Yeah, so 0.8 volts. I think I did the math wrong. Yeah. I did the math wrong. No, oh, I typed in 0.08. Yeah, sorry. Okay, so this is, excuse me, this is actually, 0.8 divided by 47 is actually 0.017. And if we multiply this as amps, if we multiply by 1,000, 1, 2, 3, we get 17 milliamps. So we can see that 47 times 4, because we have 4 of them in series, right, is 188 ohms. And again, we're adding them up. We're just adding up 47 plus 47 plus 4 because they're all in a series. And again, series is just one to another, and then this could be our voltage source, and this could be ground. There's nowhere else for it to go. All of the current has to go through one source. Whereas in parallel, you know, you can have this, and then it can go this way, and it can go this way, and this might be ground eventually, and this might be ground eventually, and it can split. And in this case, we have current splitting. So in series, we have 47 added up to 188 ohms. So 188 divided by, or into our voltage, right? Because if we want to figure out, we have voltage, we have resistance, we want to figure out current. So I is equals to voltage over resistance. So I is equals to voltage over resistance. Then we get 3.3 divided by 188. We get 0.0175. And if we multiply, so that's amps, and we get 17.5 milliamps, or we could say 17 milliamps. Right? And this all seems very repetitive, but we're kind of working it out from all different angles. And for me, it's very helpful for me to do this over and over, because we basically calculated this in every way we can, besides taking the actual current reading by breaking it open. And we can do that too. So let's do that for some more reinforcement. So I'm going to disconnect the final dude and put him off to the side. Sorry, you can't see it. I'll adjust the camera. So I took this guy out from where he was connected to the previous dude. And then what I'm going to do, let me zoom out because I need to, you need to see the multimeter. So if we turn this to current into milliamp range, right, 20 milliamps, then if we connect these together to create that circuit, we can see 16.7 milliamps, which is close enough to 17. I'm assuming there are some manufacturing like variations and stuff in the resistors, and then there's also a variance on the multimeter itself. But it's close enough, and it really illustrates how all of these are related together. One more thing, I've been using really round numbers here, like well, these are 47, so those aren't very round. But in a lot of the other calculations, it's always been 1,000 this, or 10,000 this, or 1,000, 1,000, 1,000. And especially when working on parallel, I want to do one example where we use all sorts of different values, just to make sure that you know, it's applied well. Because I feel like when it's very simplistic, it's easy to not really grasp what's happening. So I'm going to take out I'm going to put away the rest of my 47 ohm resistors, and maybe I'll keep 2 of them. I ended up putting them in a little baggie because once I tear them out of this guy that he comes in, you know, it's kind of hard to put them back. So I just get a bag and I write the value on it. So we have 2 47 ohms resistors, and let's say we get a 1000 ohm resistor. So let's throw that in there. And let's get one more random value. And this is, again, just to illustrate when we have all these different values, what we're going to get. Here's one that's 150 ohms. So I guess we could use that too. And here's a 22 ohms. That could have been useful earlier. And there's a 10 ohm too. I didn't see these before. But there's all sorts of values. So let's get a 22. And let's get a 150. So I'm going to have to test these to know what they are, but that's fine. So we know we have 47, 47, 1000, 22, and 150, I think. So let's just do some random testing, kind of like a sandbox test, right? Where we just kind of throw things together and then we can test to find out what they are. So I'm just going to connect all of these in series, and then my plan is to get a resistance test across all of them. And then we can figure out what that resistance is, and then we can try to predict what our voltage will be. And then, you know, we can just go from there. So more just, this is kind of for my benefit too, just to really understand what's going on. So we have assorted resistors here. The only one that I know what it is this one, because he's the only one that's cut. The rest, I don't know which one is which. They are color coded, but I don't know the color codes. So you could look up that on a chart. I should have mentioned that earlier. And I'm going to get from the side over here a 1000 ohm resistor separately. Let me zoom out. So we have this 1000 ohm resistor right here. And I'm going to move this to check resistance. So I'm going to move it to the number that has like close to 1000. It just has, you know, 4 whole numbers. And let's put one lead on one side and another lead on the other side, and we'll see that it says 986. So it's very close to 1000. So this guy is reading pretty accurately, and this really is a 1000 ohm resistor. So now I'm going to make sure my power is all plugged out, and it is on the opposite side. You can see here. Oh no, I just broke this guy. Ah. So our power is plugged out, and let's take this resistance reading from one end to the other, and we can actually measure all of the resistance. So we can see our total resistance here is 1250. I don't remember exactly what we used. I know we have 2 47s, I think a 22 and a 100, or a 150, and then a 1000. But what seems to be happening is we have 1250 total. So this is a very convenient way for us to test all of these. They're in series, and you can actually just take the resistance of the entire circuit. So 1250, right? So if we plug in our circuit, which we know, again, is 3.3 volts, we find that out by measuring it, and we divide it by 1250, we can predict our current. So we have 3.3 divided by 1250 is 0.00264. We times it by 1000 because this is in amps, right? And we want to get to milliamps. So we times by 1000 because 1 amp is 1000 milliamps. And we get 1, 2, 3. We get 2.64 milliamps. So let's connect this up and see if that's accurate. So I'm going to plug in my power here, positivo. And then I need to get another cable because this one just broke. You'll go in here, and then we need to ground this, right? And if we take the reading now of, let's take it from the 1000, so that, because I know this one is 1000. So we have 2.6, and again, to get the current, right, we take a known resistor. In this case, we know this is 1000, and we just measure the voltage across it, and that's 2.6. And we know that 2.6 divided by 1000 is 0.0026, which is 2.6 milliamps. And that matches nearly perfectly what we predicted would be in this entire circuit. if we measure the voltage across the entire circuit, then we're going to get 3.3 volts, right? Because that's the amount of source voltage that we have. So if we divide our 3.3 by 1250, well, we already know what that's going to be, right? It's going to be what we calculated before. So again, just measuring all this to me really helps me understand. Now what I want to do as the last part is just do this in parallel. So let's put them in parallel so that they're all going to the same row. And then we can figure out what the current is in parallel, which is, I think it's important to know because it helps us to be able to be very dynamic and create all sorts of values from resistors. So I'm putting all of these from positive. It's kind of like a weird creature. It's like a sci-fi creepy monster or something. They're all going into row 35, but I'm out of slots. So what I'm going to do is I'm going to shoot this down to another row. Okay, so I'm going to get all of these inputs, which are in parallel, right? They're all taking power from the power source, the 3.3 volts, and they're all resisting and going to this one source, and then we're going to shoot this down. And I have one more resistor to put in, or 1000 ohm resistor over here. He's hiding. So I'm going to put this one also onto this sort of line where they're all going to. And I hope I'm doing this right. So if I'm not, somebody please tell me. But so we have all of these essentially going to this cable going here, and this guy's also joining them. So he's effectively just, they're all just going to the same point. And if we take the point from here now and we ground it, then we should be able to figure out our current. Since we're going to get a current reading, we need to be able to create the circuit with our multimeter. So I'm going to put this pin back. And we can see, by the way, you can see all of them are connected to the same line. So they're all taking power. They're all reducing them individually and then going to the same line. And we're going to see what the resistance is. So this is going to be our, I guess, positive lead. And then our negative lead is the one sticking out right here. And we're going to basically, connect them together. So first, let's try and predict what this will be. So I'm pretty sure that we have a 1000 ohm resistor. I know we have an 1000 or 1000. I know we have 247s. I know we have a 150, and I think we have a 22. So what we would do is we would add all of these up together. Now, I have no idea what the common denominator is for all of these, so I'm going to just look that up. Okay, so the lowest common denominator apparently, maybe I'm doing something wrong, but it's 15510. Well, I know it has to end in 1000, I guess. So, my goodness. So what we need to do is, I forget the phrase because my math has left me, but we need to convert 1 of 47 to this number. Oh, it listed it out for me. I'm using calculatorsoup.com to do this. I just put in my fractions and it gave me this common denominator. So we have, all right, 1 out of 1000 becomes 1551 over this number. 1 over 47 becomes 33,000. And this one is also, of course, 33,000. And this is 10340. And this one becomes 7,500. So if I add those all up, we get 148,391. And this makes it look really complicated, but all we're doing is just adding fractions together, right? And this is just, unfortunately, the process to find the common denominator so we can add it up. So it's simple math, like 4th grade math or whatever, but it's just big numbers because these are all really odd numbers. So 148,391 over 155. So once we get to this point, we have to invert it again. So we just flip it, right? They just change positions. So we get 1551000 over 148,391. And if I do that, we get a value of 10. So it's 10.45. So I think it's 10 ohms that we're getting here. And 10 ohms, we have our triangle, of course, right? V, I, R. If we want to find current, then we look, V is on top of R. So I equals V over R, which equals 3.3 volts, again, because we've known this for a while now, over 10. And we get 33. No, how terrible. We get 0.33, sorry, 0.33 amps. And we times by 1,000 to get milliamps. And we get 330 milliamps, right? 1, 2, 3, we add the 0. So we should be reading 330 milliamps. So let's test it out and see if it's accurate or if I fail, which I fail often, but the key is not to stop. And now let's try and take this. So we have our guy, let's set him to 20 milliamps, and we're expecting to see 330 milliamps, or for it to explode in my face. Hopefully the first one. So we get a 1, which means it's way over, I guess. So let's change it to 200 milliamps. We get another 1. Damn, is it too high? Or am I doing something wrong? I don't think I'm supposed to go to 10 amps, because I think I need to use move this for 10 amps, but I'm kind of scared to do that. I guess I need to increase it to the 10. So maybe 200 is the max. Although, if we look down here, it says 500 milliamp max on this side. But anyway, I'm gonna move it to the side. So this one has 10 amp max. So I'm gonna move this over, and I've already moved this to 10. And let's see if we can get the reading now. We're expecting what was it? 300 milliamps, or 330 milliamps. So let's connect this together. And we get a pretty close number here. We get 0.27 amps. And we know that the value that we calculated was 0.33 amps. So it's pretty close. So since we have a bit of discrepancy and we're reading 260 milliamps instead of 330, it did make me think of something that's really important that I should have mentioned. These resistors are rated for 0.25 watts. And wattage is a unit of power. So you've heard of watts and light bulbs and all sorts of electronic components. And it's a really simple calculation. It's voltage times current equals watts. So in this circuit, I'm getting dangerously high on my 22 ohm resistors. And this is something that I really should have mentioned before because it's pretty important. So we know we have 3.3 volts. And we know that the current of a 22 ohm resistor is going to be 3.3 divided by 22. And we get 0.15 amps. So we multiply 3.3 volts times 0.15 amps, then this gives us a watts result. And the watts here is 0.495 watts. Or we could say 495 milliwatts. But this is very high because our resistors only go to their limit, the ones that I have anyway, is 0.25 watts. So I think that's why we're getting such a fluctuation on the on the current. Instead of it being 330, it's 260. And I think when I measured one of these, I won't do it again because I don't want to plug this in, but since they're getting very hot, I think, when I measured the voltage across these, I think it was 2.6. So if I do the calculation again, 2.6 volts over 22 ohms, right, to get the current, that result is 0.118 amps. So 118 milliamps. If we multiply then 2.6 volts times 0.118 amps, we get 0.307 watts. So maybe that's why the voltage is lower than it should be on this 22 ohm resistor, and I guess the one next to it, which is the same. I think these are the same. So maybe they're dissipating a lot of heat, and that affects their resistance. So anyway, something to keep in mind. You need to make sure that, don't do what I did. Don't exceed their wattage, because they were getting pretty hot, I think. So that's why I kind of cut the power, and I'm just going to look at it this way. So we were expecting 330 milliamps, but we ended up with 260, and I'm assuming it's because we were pushing two of these resistors further than they are supposed to go. So I think I'm going to end it there. There are some other little tools or components, like this guy is a potentiometer, which is a really fancy name, but all it really is a variable resistor. You can turn it up and down, and it has a range. Like this one, I think is 0 to 10,000 ohms. So I'll probably cover these in a video soon. I haven't really used it that much myself, so it'll be cool to test it out. But yeah, so that's resistance as I know it. And it's super important, of course, especially for directing the flow of electricity. So if you have any circuits where when you plug one thing in, the other one starts to lose current, then using resistors will be able to help kind of distribute that. So anyway, hope this helps. It kind of helped me to go through it again.